Okay, let's unpack this. For decades, the conversation around wind power was pretty straightforward, right?
Oh, absolutely. It was just how fast can you build the next big turbine?
Exactly. All about scale expansion, the initial investment, that capital expenditure or CapEx.
Right. But that whole era, I mean, it's really over.
We are now diving into something way more complex. This whole 25-year systemic challenge of, was it wind project lifecycle management?
LCPM, that's the acronym you'll hear. And it's the core shift.
So it's not just about the initial cost anymore.
Not at all. The industry has matured. The focus has moved from minimizing that upfront price tag to maximizing the value generated over the asset's entire life. We're talking 2 decades, maybe more.
And the only way to manage that is through what? Digitalization.
Intense digitalization and hyper-precision engineering. That's the only way.
And the scale we're talking about is just staggering. Globally, cumulative capacity is now over 11,136 gigawatts.
It is, but the real engine driving this whole transformation right now is China.
The numbers there are incredible. As of 2024, their cumulative capacity is hitting 520.7 gigawatts.
And that's not just a large number. It's a seismic shift in their energy structure. That 520.7 GW is 15.5% of their entire national power capacity.
So wind is no longer just this auxiliary supplemental source.
No, you're seeing it transition into one of the main pillars of the grid.
Which brings up this fascinating paradox I found buried in the data.
Okay.
Despite this incredibly fast, massive build-out, the national average utilization rate is holding surprisingly high, around 96%.
Right, and on the surface, that sounds like a roaring success.
It does.
But that high number is actually hiding some significant localized turbulence.
How so?
Well, consider the Northwest, where over 30% of the new capacity is being installed. The real challenge there is absorption.
Meaning getting the power from where it's made to where it's needed.
Exactly. How do you move that massive amount of new power efficiently over long distances? And how do you ensure the local grid can even handle it? If you miss that planning step, that high utilization rate becomes meaningless. You can't get the power to the consumer.
So that's why LCPM truly begins right at the drawing board.
It has to.
Okay, let's look at that starting point then. Planning. If you make a mistake, if you put a turbine in the wrong spot by just a few hundred meters, you're locking in losses for 25 years.
25 years of lost profit. It's why we're hearing terms like precision positioning.
So how far beyond just a basic weather forecast are we talking here?
Oh, we're going forensic.
Yeah.
Modern resource assessment is leveraging geographic information systems, or GIS, combined with digital elevation models, DEMS.
Okay.
This lets them model the wind flow not just generally, but on a micro-siting level. They can effectively map the aerodynamic shadow over every hillock and
Every little curve of the terrain.
precisely.
I found it interesting that they're even borrowing tools from architecture and heavy construction. Building information modeling. BIM is being used.
Yes, BIM. It's fantastic. It allows engineers to digitally construct the entire wind farm before a single shovel hits the ground.
And the critical application here is what? The wake effect.
That's the big one. Simulating the wake effect, that turbulent air, that aerodynamic shadow one turbine casts on the next one downwind.
Right. If you get that wrong, the downstream turbine just doesn't perform.
It loses significant production. So by using these BIM simulations, they can find the optimal arrangement to maximize the annual energy production, the AET, for the entire farm, not just one turbine.
So it's not just about finding where the wind blows hardest, but finding the most efficient spacing.
Exactly. And that efficiency extends to the turbine itself, which leads to this idea of one field, one policy.
A complete customization of the machine.
Absolutely. Think of it like a suit. You wouldn't wear a heavy wool suit on a tropical beach, right?
Of course not.
Wind farm conditions are incredibly diverse. Is the location exposed to intense salt spray from the coast? Is it at high altitude? Is it in a low wind speed area? The manufacturers have to customize everything, gearboxes, coatings, and especially the blades.
Could you give us a concrete example of that, like for a low wind area?
Sure. So in these low wind environments, the turbines naturally run at full power for fewer hours. To combat this, manufacturers are deploying much longer but also lighter blades.
And what did that do?
That design change lowers the cut-in wind speed, the minimum speed needed to even start generating power.
Oh, okay.
That small difference translates into many, many more full power hours over the course of a year, and that fundamentally changes the profitability of these marginal locations.
So the early stage is far more than just site selection. It's marrying the technology directly to the environment.
It has to be. And all of this precision planning has to feed into a centralized data infrastructure from day one.
That sounds crucial.
It is. LCPM is a data game. You have to implant information management systems during the development stage. This means coupling the initial asset data, where every single component was sourced, its material, its exact spec, with real-time operational data from the second you flip the switch.
And that digital coupling is the foundation for everything that comes later.
It's the foundational layer. It allows for predictive maintenance, for efficiency modeling over the next 2 decades. If you don't build that data framework early, you completely lose the opportunity for deep cost reduction later on.
Let's move from the blueprint to the build site, because if planning is complex, Section 2, the construction gauntlet, seems like a battle against gravity and physics.
It truly is a high-stakes endeavor. We are now dealing with modern turbine blades that are exceeding 100 meters.
100 meters. Just try to imagine maneuvering an object longer than a football field through mountain passes.
The logistics planning is immense, and it directly impacts that initial capex through risk and expense. You have to analyze the carrying capacity of every bridge.
The turning radius on every single corner.
Tunnel height limits. I mean, if you have to reroute or strengthen a temporary road because the blades won't fit, those costs and delays just escalate immediately. It's a specialized, expensive puzzle every time.
And then, once the components actually arrive, you have to lift them. Towers are reaching 140 meters, sometimes 200.
And then to sell the housing for the generator, it weighs hundreds of tons, and you have to lift it perfectly hundreds of feet in the air.
The operational window for that must be terrifyingly narrow.
It is. To really appreciate the precision here, hoisting these components requires incredibly strict monitoring of wind speed and direction.
How strict are we talking?
Safety protocols typically say the wind speed has to be below 8 to 10 meters per second.
That's barely a strong breeze.
Exactly. Anything stronger, and you risk a catastrophic multi-million-dollar incident. The planning isn't just about the machine, it's about controlling the climate for a few critical hours.
So the manufacturers are battling not just the build, but ensuring the turbine will withstand 25 years of stress. Which brings us to this idea of a reliability growth plan.
Yes. Reliability engineering is now being integrated into every phase. Design, factory testing, installation protocols. It's a systematic approach designed to eliminate potential risks before the turbine ever generates its first kilowatt.
The goal isn't just to make a machine that works on day one.
It's to make a machine that survives the harsh environment and the constant stress cycles of generating power for decades.
Okay, now here's where the LCPM really starts to pay off. Once the asset is built, the focus shifts to the future of smart energy management.
Right.
The old way was just traditional preventive maintenance, scheduled downtime, replacing parts based on an average lifespan, basically waiting for things to break.
Now we're in the era of the predictive flywheel. We're moving beyond prevention into predictive maintenance, or what the industry calls prognostics and health management, PHM.
And this must require a huge digital infrastructure. They're basically running massive computing operations just to keep the wind turning.
Absolutely. You need these vast high-performance computing clusters that can ingest and analyze a tremendous volume of data from hundreds of sensors all at the same time.
So walk us through how PHM actually spots a problem that a human technician just couldn't see.
Its power comes from data fusion. It takes structured data, that's your basic operational metrics like temperature and power output, your SCADA data,
Okay.
and it fuses it with unstructured data. This is the really nuanced stuff. Vibration signals from the massive gearbox, detailed chemical analysis of the lubricating oil.
It puts it all together.
It applies machine learning to these fused data sets and identifies failure risk patterns, like a slight accelerating wobble in a bearing weeks or even months before that component actually fails and causes an outage.
What's the practical impact of having that kind of foresight?
It's transformative. These PHM systems are achieving prediction accuracy greater than 85%. That directly minimizes costly, non-scheduled downtime. But just as importantly, it changes the job. Maintenance staff shift from climbing towers in risky conditions to fix broken parts, to managing data on a screen and planning interventions weeks in advance.
So it reduces high-risk human exposure and increases efficiency at the same time.
Exactly. And optimization doesn't stop once the system is installed either. The asset is always being fine-tuned.
How so?
Operators use these sophisticated localized control strategies. They're constantly adjusting blade pitch and yaw algorithms based on real-time data from that specific turbine's microenvironment. And they use unified strategies across the whole farm to dynamically manage those wake effects, maximizing output while also prolonging the asset's structural life by reducing unnecessary strain.
Okay, let's pivot to the later stages of the life cycle and the economic currents driving everything. The transition to the grid parity era, where wind has to compete without fixed subsidies, that has changed the whole profit model.
It has. Success is now tied to complex market trading, and this introduces a level of volatility and risk that LCPM has to manage.
What are the big risks?
We see three key financial risks emerging. The first is prediction deviation risk.
Meaning?
Wind is intermittent, right? That makes forecasting your power output really difficult. If a farm overestimates its output, it can face costly penalties in these liberalized power markets.
So you're penalized for being wrong about the weather.
Precisely. The second is curtailment and price risk. In regions with high penetration like the Northwest, there are times when supply just exceeds demand.
So you're making too much power.
Right. And that leads to price compression or even localized negative pricing where the farm might actually have to pay to get rid of its power during peak generation times.
And the third risk is tied to the rules of the game itself.
That's policy risk. Changes in the speed of market liberalization or new fees like auxiliary service fees for grid stabilization, they directly impact the long-term internal rate of return, the IRR. Project owners have to continuously model how these regulatory changes are going to eat into their future profits.
This volatility makes the next LCPM phase asset renewal a massive gamble, but also a huge opportunity. We're seeing this big for small strategy emerge for older wind farms.
This strategy is vital where land and grid connections are scarce. Instead of tearing down and walking away, owners replace a large number of small, aging turbines with far fewer, but massively larger and more efficient ones.
Is there a good example of this?
Yeah, the Chongqing Sinoping project. They took out 35 old units, each generating only 850 kilowatts. They replaced them with just 21 new units that could generate between 3.6 and 5 megawatts each.
That sounds like an instant massive leap in efficiency. So what's the financial catch? Why isn't every old wind farm doing this right now?
Well, the catch is profitability modeling. Historically, these farms were built under fixed subsidy regimes. Some of these older regions cap the number of subsidized generation hours, maybe at 2,000 hours a year.
Okay.
So while the new turbines generate exponentially more power, the output beyond those capped hours has to be sold at the volatile, lower market price. The financial viability of the entire retrofit, its IRR, is heavily dependent on those fluctuating market prices. It's a major risk.
Let's shift gears to the highest stakes sector, offshore wind. That must present some unique LCPM challenges.
It does. Offshore projects thrive because the wind speeds are often 20% higher and way more stable than onshore. This means much longer annual generation times.
And they're closer to where people live, right?
In places like China's developed East Coast, yes. They're closer to major population centers, which reduces transmission loss.
But the LCPM requirements, they must be exponentially tougher given that environment.
They're extreme. You've got high salt content, constant humidity, the risk of typhoons. That demands that engineering and anti-corrosion standards are established on day one. Every single component has to be designed to resist corrosion and fatigue in a way onshore assets never need to.
A maintenance failure offshore isn't just costly.
No, it requires specialized vessels, specialized crews. It multiplies the operational expense exponentially.
And finally, the life cycle closes with decommissioning. We don't often think about the end of life, but it's a really complex decision point.
It is. The first optimization path is usually life extension. By using all that historical data gathered over 20 years, plus real-time structural health monitoring, owners can often show that the asset is viable for another 5, maybe 10 years.
And that's the lowest cost way to maximize the final value.
By far. But when an asset absolutely must retire, there is a looming environmental and logistical headache.
You're talking about the blades?
The blades. That is the crucial, unresolved technological challenge. The materials are largely composite fiberglass and resins, which are extremely difficult and expensive to recycle harmlessly.
And as this first massive generation of turbines begins to age out,
The industry must urgently find solutions for the resource utilization of those colossal blades. It is the final engineering and economic hurdle in the entire life cycle.
so if we connect all these pieces, it's really clear that the success of a modern wind project isn't defined by the steel and concrete you install in year 3. It's defined by the systemic, digitized vision you maintain for 25 years.
That's the perfect synthesis. The economic success now flows primarily from digitalization, that 85% predictive accuracy, the continuous data management, rather than from just marginal savings on initial hardware costs. LCPM is a discipline that demands balancing early planning precision, high difficulty construction safety, deep operational data management, and the financial agility you need to navigate these complex market economics.
It's a remarkable evolution, watching this industry transition from pure, heavy infrastructure to really heavy data science. The integration of advanced sensing and self-adaptive control means the wind farm is fundamentally changing. It's moving from being a passive power generation unit to becoming a self-regulating, grid-friendly, smart energy station. This raises an important question for you to consider. If these power sources can self-regulate and adapt their output instantly, how will that profound change influence the fundamental stability and reliability requirements of our entire electrical grid ecosystem?